Hi everyone, today we're going to be learning about topic 6.3, heat transfer and thermal equilibrium. Now the concept of energy transfer or heat transfer is something that we deal with in our everyday lives whether or not we necessarily know it or not, and it's actually quite straightforward. So what it says is that energy as heat, which if we remember, heat is represented by Q, transfers spontaneously from hotter objects, basically objects that have a high temperature, so T is high, to colder objects. So where temperature is low, T is low, through collisions. All right, and so we can imagine, let's say I have a particle here. I have a particle here. Let's say this is at 300 Kelvin, and this is at 273 Kelvin. This particle is moving in this direction. It's going to come over, and it's going to collide with this particle that's at 273 degrees Kelvin. What'll happen is that through that contact, you'll have some energy transfer. And so let's say if this is at 273 and 300, we'll have this one lower to about 290 Kelvin, and maybe this one over here is now at 283 Kelvin. And so the heat has transferred from the hotter object to the colder object. And again, what we mean by spontaneously, what we mean by that is that it happens without external force. So I'm not applying some sort of a force here to transfer energy. It happens spontaneously. It happens without any outside energy. One important thing to note is that the heat transfer will continue until all objects have the same average kinetic energy. Right? If they have all the same average kinetic energy, at that point the heat transfer will stop. And the way that we measure this is that we measure through temperature. And so, in other words, when objects in a contact reach what is known as thermal equilibrium, it's a very important term there, thermal equilibrium, they will have the same temperature. And so in this scenario, let's say I have a block. This is at 400 Kelvin. I have another block over here, and this is at 300 Kelvin. What I can do is I can put these two blocks in contact with each other and then wait some amount of time, right? T is time. I'll wait some amount of time. At a certain point, the heat will transfer from my hot object to my cold object, and these will be somewhere in the middle. Let's say 350 Kelvin. And so once they're at the same temperature, they have the same average kinetic energy, or KE. That means that they've reached thermal equilibrium with each other. And of course, it's always going to flow from the hot object to the cold object. And as a reminder as well, our kinetic energy is equal to 1/2 mv squared. Now, it's important to note that the heat released by one object is equal to the heat absorbed by the other object. We can also represent this in a more mathematical format by saying Q of A, or the heat of A, is equal to negative Q of B. The heat released by A is equal to the heat absorbed by B, and the sign of those should just be reversed. If you want to relate that to what we were seeing in our previous videos, Q system is equal to negative Q of surroundings. That is basically saying that if I have some sort of a system, if that is releasing heat into its surroundings, it's going to be equal to the same amount of heat that's absorbed by that surroundings, and we just represent that by a negative sign right here. So Q system is equal to negative Q surroundings. Now, one important thing that we need to keep in mind is that temperature changes will not be the same due to something called specific heat, which we'll talk a lot more about in our next video. But the specific heat of the specific heat of a particular object is going to determine how much the temperature actually changes, right? So in our previous example, it may not be the case that if I have, right, block A, which is at 400 Kelvin, and block B, which is at 300 Kelvin, it may not be that every single time they're going to be, if I put them in thermal equilibrium with each other, that block A and B together are going to be at 350 Kelvin, right? Somewhere right in the middle. It's going to depend on the objects in contact. So if I put, for example, a piece of hot gold with a piece of cold aluminum, that's going to be different, or at least the temperature that they end at is going to be different than, for example, a piece of hot gold and a piece of cold copper. And so we'll get a lot more into that in our next video, but for now, the most important thing to remember is that because of the specific heat, the temperature at which you end is going to really depend on the object that you're studying. Now, we've already talked a lot about kinetic energy in a previous unit, and that's going to kind of come back now. And that's with these Maxwell-Boltzmann distributions. If we remember, the kinetic energy for each sample can basically be shown using a Maxwell-Boltzmann distribution, where V is our average velocity of particles, and N is equal to the number of particles. And so anywhere on these curves is basically the average velocity of particles at that particular number of particles. And each of these lines correspond to a different temperature. We'll have a little bit more practice with this in class, but for now, that's all. Thanks, guys.